In the Dirac-Lagrangian and in the Dirac equation, which we obtain by taking the classical limit, we have this constant gamma mu, which we saw has to be a 4 by 4 matrix if we want, in the classical limit, that psi obeys also the Klein-Gordon equation. So this means that psi has to be an object with 4 components. However, psi is not itself a 4 vector, a Lorentz 4 vector. That is, it doesn't transform as a 4 vector under Lorentz transformation. In fact, under Lorentz transformation, it transforms as a 4 spinor. We will see later how a 4 spinor transforms under Lorentz transformation. For the moment, let's see how many degrees of freedom we can encode into a 4 spinor. And we don't need to be quantum for that, so let's start from the Dirac equation for classical fields. And the trick is to go in a specific frame where the calculations will be made easier. And the easiest frame we can think of is a rest frame, so the frame where a particle will be at rest. So in this frame, the energy momentum 4 vector is simply, for the time-like component, the energy equal to the mass, mc squared, but c is equal to 1. And because the particle is at rest, there is no momentum, so p equals 0. But that doesn't help us much because we have k mu here, but there is no k mu in the Dirac equation. But that's because we express the field as a function of space-time. If we Fourier transform this equation, however, we will naturally have the energy momentum which will appear. So here is our k mu. Now the derivative is only acting on the exponential, because that's only where we have x now, and that's going to bring down minus I k mu. So that's the Fourier transform of our initial left-hand side. Therefore, we have that's the Dirac equation in momentum space. Now, going to the rest frame, we see that only mu equals 0 survives. Gamma naught is a 4 by 4 matrix. Therefore, the identity is also a 4 by 4 matrix. So we see that applying this matrix to psi imposes that its two lower components must be 0. In other words, despite the fact that we have a 4 spinor, we have only 2 independent degrees of freedom. Therefore, a 4 spinor only encodes 2 degrees of freedom. This we showed in the rest frame, but of course, if there is only 2 degrees of freedom in one frame, that should be true in any inertial frame, and therefore we can generalize that to any frame. So what is the spin which only requires 2 degrees of freedom? Well, that's the spin 1/2, because we have either spin up or spin down. Note that we already had an indication that the Dirac-Lagrangian and the Dirac equation will describe spin 1/2 object. And that's because the spin operator for spin 1/2 is half of the Pauli matrix. And we saw that the gamma matrices are themselves function of these Pauli matrices. But all these are only indication that 4 spinor encodes only a spin 1/2 object. If I want to show properly that this is indeed the case, we will need to look at how a spin 1/2 transforms under Lorentz transformation, and then see that our 4 spinor indeed transforms that way. So we are not going to do that because that will take us too far. However, I will give you how a 4 spinor transforms under Lorentz transformation, because that we'll use for applications, for instance, to show the spin-orbit interaction in atoms or in nuclei. In case of a boost, for instance, we go from one frame to another which is moving at constant velocity v with respect to the first frame. And that's how a 4 spinor will indeed transform. You may wonder where the velocity v appears here, but remember that nabla is just an Euclidean momentum and divided by the mass that gives us velocity. And the sigma with an arrow is a short notation for three vector made of the three Pauli matrices.